So as she said, I titled my talk here, Running That on What? One of the reasons I decided to explore this topic is because my history is as a Linux systems administrator. So I did that for about 15 years. And I spent a lot of time working on open source projects. So I've been working on open source longer than I actually had a job. So I've been working on open source for about 20 years. I wrote a couple of books, as was mentioned, on Ubuntu, Linux, and OpenStack. But one of the things I really love doing is playing with weird hardware. So I used to do it a lot more when I had more free time in my 20s, less of it now. But I joined IBM 2 years ago to work on mainframes. My history is in distributed systems. So I was working on clouds and doing OpenStack and doing like lots of DevOps and SRE type work throughout my career. But I wanted to change after I left a container startup. I was like, I've been doing like, the Linux thing and the OpenStack thing. I started getting into Kubernetes, but I wanted something different and interesting. So when the folks at IBM reached out to me and said, hey, you want to work on mainframes? I said, no. But really, when I started digging into the technology, I'm like, actually, this is really super cool. And the one thing about mainframes is they are not X86. So the first thing that I encountered when I was learning about these machines, which I knew nothing about when they reached out to me, was that you have to compile your software specifically for IBM Z. And I'm like, that'll be an interesting challenge. So in my role, I work with a lot of open source projects to port their software over to the platform. And my own history has a lot of weird hardware in it. So these are some pictures from my house. These are all machines built in like the 90s. 2 of them are Sun boxes. So the tower there is an Ultra 10. It's a SPARC 64 architecture. It's currently running Linux, but in the past, but it's a really old version of Linux. I actually need to have a project to reinstall it with BSD, which is now supported. But that machine, it's 450 megahertz, has like 2 gigs of RAM, and it's a lot of fun to play with because the thing's like 25 years old, but everything still works on it, which is astonishing. And it's pretty quick for what it is. The other 2 pictures are actually from my husband's collection, which is taking up so much space. It's a couple of SPARC 32s. So those are 32-bit SPARC architecture, and then an SGI Challenge, which is a different architecture from SPARC. That's a RISC-V architecture. So these are all old, and if you walked into a data center today, you probably would not see any of these 3 architectures. Most of the systems, they're not even supported anymore. I think you'd be hard-pressed to find something that ran on SPARC 32. Even my SPARC 64 box, there's no Linuxes that are currently supported for it. But at the time when these were very popular machines, people were really into installing Linux on everything. So this image here of installing Linux on a dead Badger, that was a funny essay written at the end of the 90s where people were installing Linux on everything. They were recompiling Linux because it was open source. And when you have the source code, you can compile your code for whatever architecture you want and see what happens. So that was a fun time. But then we kind of consolidated on x86. When you walked into a data center, you were seeing these different architectures less and less. And even on consumer devices. These are a few examples on this slide. Also, I have kids that like to play with my computers. So Mac, the MacBook Pro, until just recently ran on x86. It actually ran on Power, which we'll talk about a little bit. In the 90s and into the 2000s a little bit, it ran on Power, but then they switched to x86. The second picture here with all the wires in it, that's a 1U server that's sitting in a home office. And that's like the standard kind of server you'll find if you walk into a data center. It's what all the clouds are running on, like just standard server stuff. And this picture on the bottom, it's actually a netbook from 2010. And the netbooks were exciting because they were Atom processors, but that's still a 32-bit x86. The thing with Atom is they were slightly lower power and they used less power. So the battery life on these little netbooks that were very popular for a few years, they had great battery life, but ultimately still x86. But now we're starting to see a bunch of architectures sort of popping up, and some of them never really left. So this is kind of a not a true story. Like, we consolidated on x86, but there are still other architectures that have always been around. It's the one that I work on, IBM Z. It's the S390X architecture. It's like the great grandchild of the first mainframe released in 1964. So like code that was written back then, with a little tweaking, will still run essentially on the machines of today, which is kind of amazing. We work with some really interesting clients who have some really old code that still runs from a very long time ago, long before I was born. So these machines, they're big, and the latest ones like fit into a 19-inch rack space. So they're 19 inches wide. So they fit into a normal spot in your data center, but they're tall, like they take up the whole slot, right? They're not like the blade servers that you're familiar with. I briefly mentioned power. So PowerPC is what used to power Macs. A bunch of the gaming systems, I think like the PS2 was PowerPC back in the day. And so like power has been around for a long time, but some of the things moved away from it, and some things are moving towards it. And a couple of years ago, it was open source. So there's now an open power project. So you're able to get the source code, or the source diagrams for running your own power chipset. So those two have been around for a very long time, and they have evolved. But one of the things that's really been transformational in the past couple of years has been ARM. So ARM is really taking the world by storm. The first time I encountered it actually was with the Raspberry Pi. So the first Raspberry Pi was an ARM chipset. This is the Raspberry Pi 4 sitting on my desk. That one's got like, this one, I think I have the 4 gig version. So it's actually like a mini desktop, but it runs Linux. You can run like a bunch of different Linux distros on it, but it is a different architecture from x86. So like I can't install Chrome on it because Chrome is a proprietary browser that Google has not ported to ARM, for instance. So I can run Chromium, I can run Firefox, because those have been compiled for the Pi and ARM, but I can't run some of the proprietary software that the vendor has not ported. Our phones, they are all ARM. Whether you have an iPhone or an Android, they are ARM. So one of the benefits of the ARM architecture is it is really fast and powerful, but it's also low power. Which is why it makes sense for the Raspberry Pi, which you just connect with USB. It makes sense for phones because you want your phone battery to last a really long time. And like the mobile manufacturers have put a lot of time and money, obviously, into making sure your battery life is good on your phone. And then some of the most interesting news for me in the past year was that the new Apple systems with the M1 processor, that is also ARM. And again, just like with the cell phones, one of the reasons Apple went with ARM was because of battery life. These processors are really good with battery. They're low power, and they're fast, and it's a compelling option. But it was fascinating to see because they, as I said, like they used to run power, then they ran x86, and now they're doing ARM. And as a very consumer device that people expect to work flawlessly because it's an Apple product, it was an interesting move for them. And I've been super excited about it because I like seeing other architectures out there. So as I go through these, you'll see what kind of came to pass was that x86, it's cheap, commodity, very like, across the board, it's just good hardware for general purpose. But then if you get to Z and Power and ARM, like they all have specializations. So it makes more sense for some products to be on specialized hardware, because suddenly, Apple decided they wanted better battery life, right? Or if you're working on Z, like maybe you have workloads that perform better. So like on Z, one of the things that it's really good at is data processing, because the CPUs have really huge caches. So it turns out that it's really good for crypto. Like I tell people, if you were to build like a Bitcoin machine, it would look a lot like a mainframe because they are essentially built to do crypto. They have like onboard crypto cards. They have huge caches in the CPUs. So all of these new architectures, these old architectures, the architectures that we're increasingly going to be encountering in our jobs, they are all specialized for certain purposes, and companies are coming back to finding value in that. So to quickly step back from all the pretty pictures and all the hardware stuff, I'm going to go a little 101 here. I will say that like this whole talk is a very high level talk. We are really speaking to developers who are not super familiar with other architectures or have only played with them a little bit. So at the end, I'm going to have like a bunch of terms that you're going to want to search for to learn more. But if you're a hardware guru already, this may be a little boring for you, but so that's just a warning. But essentially, when you're compiling hardware, like today, like as I say, like the commodity architecture is 64-bit x86. The instructions for x86 were developed like the late 70s, released in the early 80s. And if you ever are interested in x86 history, it's really, really interesting because it wasn't actually the best option at the time. It was the one that was ready when IBM wanted to release their PCs. Like they're like, okay, you guys have been over here working on this other instruction set, but it's not ready yet, so we're just going to go with x86. And it kind of took off everywhere. IBM released the first like personal computer, and it's actually one that I had because my uncle worked at IBM. And then there were IBM like clones, and that's kind of what the first PCs were, and they were all x86. And since we all sort of consolidated on x86 in the 2000s, most developers don't even pay attention to the architecture, which is why I'm here. And this slide, the pendant in me doesn't love this slide as much as I could, because it's not, like strictly speaking, like in classic computing, like all the hardware really understands is like ones and zeros. Technically, they actually understand words, but when we're talking at like the transistor level, like it's ones and zeros. When you talk about how many transistors can fit on a chipset, what you're talking about is those ones and zeros that eventually everything gets turned into. I mentioned classic computing here. Quantum computing is actually, they have more states than ones and zeros. So don't leave yet, but afterwards, if you want to look up quantum computing, it's super interesting and a lot of fun. And there's some free resources out there. You can actually play with a quantum computer. Anyway, not this talk. So what compilers, in the case of things like C and compiled languages, and interpreters in languages like Python, they take your human readable code, they process it and turn it into the words that the computer can understand, the hardware, and then the hardware at some point, just turns it into ones and zeros. So the code that you see is really just your first step in the process. And then the code gets compiled down through the levels in your system until it finally gets to the silicon. So I briefly mentioned open source. So when you have open source software, you have access to that human readable code. It's available and it's out there, and you're able to download it and make changes to it. But for the purpose of architecture, the really important thing is that you're able to compile it yourself for whatever architecture you want to be targeting. I did a workshop a few weeks ago where we just went and downloaded this random open source Tetris project. It was written in C. We put it on an IBM Z Linux machine, and we compiled the software and started playing Tetris on the mainframe, because obviously, like, you have the power of a mainframe. What are you going to do with that? I played Tetris. So you can grab code and see if it runs. And I've had very good luck, but there are some gotchas when you're compiling code, and that's what I'm talking about here. But as I say, like with the open source software, you are able to compile the code yourself. So whatever machine you have around, you can write the software for that code. You don't have to wait around for your vendor to write a binary, or if they never will. Like I'm not holding my breath for Google to release Chrome for the Raspberry Pi. It's just not their market. In order to release for a specific hardware target, they actually have to have build systems and make sure it's properly tested for releasing and everything. And a lot of companies just don't want to do that because they don't see the market very big. In the case of the M1 from Apple, like a lot of companies are going to have to start building for that because MacBook Pros are very popular machines. I did mention this a little bit, but an important thing when you're considering developing for non-x86 platforms is like the level of your language. So you hear like higher level versus lower level languages, and a lot of people sort of take this opportunity to say that the lower level languages are harder, and you have to be a better programmer to write in them, and you have to be super smart and stuff. But like that, I haven't actually found to be particularly true. The real difference between like the higher level, the lower level languages is like, it's right in the name. It's how close they are to the hardware. And so in like a lower level language like C or C++ or assembly, which is very low level, they are like you can actually interact with the hardware in a real way. And so with these languages, you may run into problems when you're running your code on a different architecture. And these ones, by far, like when I'm working with open source projects, these are the ones that I run into where people have the most trouble porting the software from one of these languages into something for Z or ARM, because they end up taking advantage of optimizations from the hardware, especially in the case of something like assembly. Assembly really is tied to the hardware. So porting something from assembly on x86 to something on Z or Power is really, it takes a lot of work. And one thing I'll talk about a little bit is like sometimes people embed assembly code inside of their C code because they're trying to do something clever, and that's tough when we're trying to port the software. The higher level languages are a bit further from the hardware, so they don't. From a developer perspective, they often don't care where they run. You do have to have an interpreter for that hardware, but things like Python and Node and Java, like they all have compilers or interpreters for these major platforms that I mentioned. So you can run any of these on Z or whatever. Since they don't tend to get into like the guts of the hardware, like things you write in Python usually just work. And then where it doesn't work, I found that you'll often see like C errors, which is kind of funny because what it did is it called out to something that was written in C, and that didn't quite work on the architecture. But for the most part, I've had a lot of luck porting Python code and stuff. So much so that one of the projects that I work on is written in Python with Flask. And we mostly tested on x86, even though the target is Z.
So just it's not a question that came in the chat, but just my own question that maybe other people have kind of coming out. There was a lot of developer chatter on Twitter about, homebrew breaking and like other things because C was inside of it like that. Or
what was it again? I'm sorry.
Some of the installers for different dependencies in Ruby and Python, people thought they were far enough from the hardware. When we saw ARM and M1 come out, suddenly people had these brand new Macs. They couldn't install anything. So I'm just wondering, out of curiosity, if it was kind of something that was wrapped in there that was probably the problem.
Yeah. So, I mean, a lot of like, I don't know how much of a heads up Apple gave the vendors who were writing software for the Macs. Like, I don't know how much warning they gave them, because it was a big announcement and they tend to keep really things under wraps. So what they did was Apple wrote like a conversion thing, so it can convert. It's like an emulation layer, which emulates x86 and tries to run the applications that are written for x86 on the machine. And they're like, oh, it runs just as fast. It's great. But it like sometimes there's weird stuff. And of course, they didn't test every piece of software in the world. So yeah, like people were running into issues, and Apple is fixing them as quickly as possible and working with vendors to recompile software. And like, this is going to be a big job for a very long time, which is one of the reasons I was surprised that they made this switch, because it's going to be tough. And yeah, so like some applications, yeah, like if they thought they were far enough from the hardware and it's just going to work, but you run into issues sometimes, for sure.
We also have a couple other questions. Someone saying, so if you're a higher level programmer, and you wanted to learn C++, is it recommended now to check if your hardware is compatible? And they're asking kind of like, what would be the kind of requirements for your operating system? With the caveat that they don't know much about hardware. So
yeah, no worries. So I'd really start, if you are learning just a new language, just like start wherever you are. So like if you're on, I'm on a ThinkPad, an old x86 machine running Linux. If you're on a brand new M1, an Apple Mac, like just start working there. And then once you get more curious, then you can start paying attention to architectures and start building things in other places, unless of course you're developing for something else, and then you should test it on that. But I will talk a little bit about how you can test software on other platforms. So we'll get there.
Thank you so much.
All right, any other questions?
But it might require more knowledge than we can give right now, and you might cover it a bit later. They're just saying, well, then probably a virtual machine with Ubuntu wouldn't work on the new MacBooks, would it?
So it depends on what virtualization technology you're using. It might, because if you are emulating x86, it should work fine. But yeah, like natively, if you're not running an ARM build of Ubuntu, it won't work.
No, I think that's all the questions for now.
Okay, but yeah, there's definitely a way to run them right now, but I think it's just doing emulation. So.
Yeah. So
this is kind of the meat of the talk here. Is that so? What do you do as a developer now? So my first piece of advice is that you could do nothing and just keep doing what you're doing. A lot of some people, if anyone on this call is a like a mobile app developer, don't feel bad if you didn't know that your phone is ARM. Like, no one pays attention to this. When you're doing mobile app development, like Apple and Google and like the other parties involved, they've worked really hard to make it as transparent as possible for developers. They have SDKs, they have really well-tested languages, and so you're just writing to the platform, and it doesn't matter what the architecture is, because your ecosystem for developer tooling has already solved that problem for you. And you're probably not likely to run the app that you developed for your phone on your desktop directly. So they're very different platforms, and people do different things with them. Apple has actually, I was talking to someone when they were reviewing my slides, and they mentioned that Apple has actually been trying to do some of that stuff, and that may be one of the reasons, because the iPhone is ARM and now the new MacBooks are ARM, and they're going to try to do some crossover there. But day-to-day developers, mostly if you're developing an app for the phone, you're developing an app for the phone. If you're writing something for the PC, you're writing something else. So you might not run into issues if you're this kind of developer. But one of the things I will say is I believe that being aware of different architectures and being curious about these things it's going to make you a better programmer, because you are going to understand your environment more, and you can break out of the little sandbox that the companies have put you in for developing software. But if you don't want to, that's okay too. another thing, like, so if you do want to dig into this, you can learn about the architecture specific components of the language that you're using. And I'll have some terms at the end of the deck of things you can look up to learn a bit more, and so you know what to search for. But one of the things I'll say, like, if you want to develop across like all the platforms, like, learn a bit about these components and like be really mindful about how you use them. Like, if you find like, oh, like this will like double the speed of my application if I use this hardware acceleration on x86, maybe that's going to be worth it. But if you want this to be used on other platforms, maybe you don't use that. Maybe you write a conditional in your software that actually looks to see what hardware is being used. And maybe you really don't care about it running on anything ever, but maybe you should document that because there's people like me out there who are trying to port your software and we run into an error and we're like, oh, what did they do? It'd be really nice if we just popped open the source code and said, hey, we're like exiting out to this x86 specific thing. Like, let's, and now you can't do it. Some of the best ported software I've seen, they use conditionals, as I said. So like, if it's on x86 and using like AES encryption, like it'll pop out to, you know, the hardware stuff in x86 that does that. If it detects it's on Z, it'll pop out to the AES encryption in the hardware on Z, which is what Go does, the language. You can use like the hardware encryption on Z, which is super cool. Or if it's not using any of those, it'll fall back on software to do the encryption. So then if you're on x86, it uses the hardware. If you're on Z, it uses the hardware. If you're on ARM, it just does it in software. And then it's a little bit slower, but at least you're able to run it on all of these architectures. Some of the things that you want to avoid making assumptions about are these terms like pointer sizes and byte ordering. So pointer sizers differ between architectures, and the order in which the bytes of files and packets and things are read differs on architectures as well. So this is like really low level hardware stuff, like the order in which a file is read. Like sometimes they are not the same across architectures. So someone trying to be really clever will be like, oh, read the first, X bytes of this file and do this thing with it. Well, if you change architectures, those first 4 bytes may be different because it's reading them in a different way. And as I say, document the usage. Like if you use something that's x86 specific, call that out in the source code. I'd say avoid like using like sneaky tricks with like the CPU specific instructions and things like caching. Like people will stash stuff in caches sometimes, and you can't really rely on that being available on every architecture. Some developers love getting really like nerdy with assembler, and so they'll like try to like over optimize their code, and so they'll drop into assembly language in order to do certain tasks. And like if you really need to do that, it's okay. Don't do it for like learning's sake. Do it if you really have to. But it turns out like modern compilers are like, they're really smart. So if you're over optimizing your code, like maybe look and see if your language actually requires that, or if there's already mechanisms in place to do that. Another thing that we run into, even when we're like, the work I've done like modernizing code, like taking code from 10 years ago and bringing up to speed with the latest compilers, is that like people do tricks. And like they did tricks when they wrote the code 20 years ago, and they don't work on the compiler today because they're making different assumptions. So even on an x86 system through the years, like the modern compilers work in different ways. And so they're pretty smart and they solved a lot of problems. So if you're trying to be sneaky about things, like it may not always work to your advantage. And also like hardware enumeration, like like what hardware is actually in a machine. So you may assume like every computer has, some sort of network device and some sort of attached storage or something. But like on a mainframe, the networking is very different. The attached storage, the mainframe doesn't have storage inside of its box. Everything is offsite. So if you're relying on that inside of your code, it's going to fail when it tries to use a computer that has something different on it. And memory regions is a big thing. Like some architectures allow the CPU to like like go to every piece of the memory in the system, and some of them are more boxed in, so they're not, the CPUs don't have access to all the memory. And so if you're making assumptions about the memory space, it may not be valid across architectures. So sort of coming to the end here, but a couple of things if you want to play around with other architectures for cheap. If you don't already have a Raspberry Pi, a lot of people have them. They are super fun. You can get one that's essentially like a mini desktop. It's got 4 gigs of RAM for about $100. I think the board itself costs like $50 maybe, and then you have to get like a power cord, and you have to get an SD card to put the operating system on. You have to get like a bunch of pieces together. There's a bunch of kits out there that have all of the hardware you need to assemble to put a Raspberry Pi together, but it's about $100. A bunch of different Linux distros will run on it. On mine, I'm running Raspbian, which is a Raspberry Pi version of Debian, but Ubuntu runs on it now, and there's a bunch of others. Oh my gosh, I should have brought it down here. There's like a little keyboard. It looks like a keyboard, but it has a Raspberry Pi 4 built into it. That's super cool. So like the keyboard is your computer. I wish I brought it down here. It's really cute. Anyway, that one I think is like $80, and that has everything except for the power cable. And it doesn't have a mouse, but it is a keyboard. So. And then also for work with open source projects that I do, Z, the architecture S390X, we give out VMs for 120 days in our Linux One community cloud. That's hosted at Marist College in New York. So you can play with Linux virtual machine, and we're super generous with how much resources you get. I think we give you like a bunch of RAM and a bunch of hardware space or hard drive space. So these VMs are pretty cool. And you can try, compiling your software on Z, and like with all these like it's just Linux. Like if you're running Linux on the Raspberry Pi, it's Linux. If you're running it on a mainframe, it's Linux. So you'll get this VM and you'll be like, okay, it's Linux. What do I do now? Like what you do now is you grab some open source software and see if it builds and play around with it. Maybe play with your own software on it. Install Python, write some programs, have some fun. So those are a couple of ways you can try running your own stuff. So from here, if you want to learn more and go down this rabbit hole that is hardware, a few terms you may want to start searching for. This list is like super random and like things that I came up with, and people who reviewed my slides, they threw in some here and there. Even I don't understand all of this stuff on here. But having a basic understanding of some of these terms will get you pretty far. And once you start reading about one, you'll find about another. So like if you start reading about RISC and CISC, so RISC is like the ARM processors, CISC is x86, for instance. But like if you start reading about those terms, you're going to learn about conditional execution. You're going to learn about hyperthreading. You're quickly going to run into the term ISA, which is an instruction set architecture, which are kind of like the instructions on how the hardware CPUs are working. Hardware registers are pretty much how the software talks to the hardware, so that's really important to learn stuff about. And then you have things like the CPU cache, endianness. So on Z and some of the power systems, you have big endian, which refers to memory ordering. Most architectures you'll encounter these days are little endian. So in my job, I sometimes run into endian problems. So looking up that's an interesting rabbit hole to go down. But again, like once you start reading about this stuff, you'll learn and run into other terms. But this is like a good starting place because this stuff is really the core of what you're going to run into when you're porting. So I'm going to wrap up here. Do we have any more questions?
There was a question that was about, it seems kind of more of an opinion. They say, I'm a hardware developer. I see that most times we can't use fancy architecture or coding algorithms on C, but we're still asked interview questions about it. Why do you feel that's the case?
That's a good question. I mean, they may be trying to probe your knowledge about like hardware awareness, because as I say, like most developers don't pay much attention to other architectures, and so the interviewer may be trying to gauge your awareness of that. I don't know, see how open you are to trying to develop on other architectures.
That's fair. Does anyone else have any other questions? We've got a couple minutes, so if you have anything, please put it in the chat. While we wait to see if anyone rustles some questions out of their knapsack, I will say I have seen that keyboard computer hardware thing, and I was really excited. And then I was like, but is it really? The whole computer is just in the keyboard, or are they just tricking me for like online promotion and propaganda? So I never ordered it.
Yeah, it was out of stock for a long time. I finally got one over Christmas, and I was so excited. I have no use for it. Like, I have way too many computers. I don't even know what I'm going to do with it, but it was so cool. I had to have one.
Yeah, that's awesome though. Oh, someone in the chat wants one too.
Yeah, I'm gonna try to find the link to this real quick. I think it's called the Raspberry Pi Desktop.
Let's see if we can.
No, that's not it. Oh, it's called the Raspberry Pi Keyboard. No, that is not what I'm looking. Oh yeah, here we go. And my screen go.
Another question. Oh, there's the link. When a program doesn't work due to architecture, are there common solutions or approaches we can take?
So the first thing you want to do is just read the error message, because it turns out that's going to be super useful. Sometimes when I'm debugging, like over time, like the error messages become familiar, and some of the decisions, like if you start working with C a lot, you're going to notice error messages, and then you're going to eventually learn about why a decision was made. Because the first thing I learned when I was working with people porting software in C was that like they have like this knowledge stuck in their heads of like all these common things, and they're like, oh yeah, you know, that happens because back in 2003, like GCC made a decision that impacts big endianness. Or something. So a lot of the knowledge is really just stuff you have to gather. I don't have like a list, which is something I really wish that some of my colleagues and I could put together, especially with the little endian, big endian stuff we encounter. But for sure, like error messages are very good. And that's going to be where you want to start. I wouldn't say there are like common solutions, because the gotchas are really all over the place. Some of them are with networking, and some of them are with, you know, as I said, like memory or caching and stuff. So they're all over the place.
Well, thank you for offering the tips. It's been a really interesting talk. I'm really glad that you're paying attention to the hardware. Like you said, not a lot of folks are, and it's gotten a little weird out there. Oh, we do have another question. If you have more questions, drop them in the chat. We have like 120 seconds to do them. When you can't debug on a device, how do you debug problems in code other than printing?
That's a good question. So you might encounter this on something like an Arduino, but I mean, you essentially do need to find a way to get those error messages out. I don't know. I should ask some of my embedded developer friends how they go about it, because I'm not sure. It's a good question.
Something else to explore after the chat. But thank you again, Elizabeth. It's been amazing. Thanks to everyone who came and had these great questions. We will be switching over to the next session in a couple of minutes. So if you want to switch out to another session, just click on Sessions on the left-hand side there. And I think your screen is still up, but we have Liz saying, fantastic session. Thank you so much, Elizabeth. Suzanne is wondering if the presentation will be available somewhere.
I'm going to tweet out the slide deck, but if anyone else, I think the video will be shared at some point too. So yeah.
Amazing. Thank you.
You can find me online. My website's princessleia.com, so I'm easy to find. But yeah, feel free to reach out. Thanks for coming.
Thanks, everyone. See you.